Hey, welcome. So in this video, we're going to be looking at how LIGO uses interferometers to detect gravitational waves. Gravitational waves are really useful to help us understand the nature of black holes and neutron stars and other astronomical bodies, right? So as the binary system merge, they emit gravitational waves, which could give us insights into their mass, their distance, like redshifts, etc., right? Which could be really helpful into our understanding in physics. So hopefully by the end of the video, you'll know a little bit more about interferometers and how we discover or how we detect gravitational waves. So yeah, let's go, roll the intro. Interferometers are very intricate and delicate machines, and in this video today we're gonna discover the science of how they work, and we're gonna find out how they detect gravitational waves. Okay, so you have here is a diagram of an interferometer, and you have a laser emitter here which sends out lasers to this beam splitter, and it splits the beams, right? So half the beams would pass through it and get sent that way, and half would reflect and get sent that way. Okay, and you have mirrors here and here, and they would reflect the beams back to the beam splitter, which would now rejoin the beams, and then they would get sent to the detector. Okay, so normally when there's no gravitational waves passing through them, they would the two waves, the two lasers would be in phase. That means that well, they obviously have the same frequency and amplitude in the first place, right? And when they rejoin, they would look something like this, right? They would overlap each other exactly. And according to the principle of superposition, it states that if waves from two sources occupy the same region of space at the same time, then the displacement at any one point is the vector sum of the individual displacement at that point. Therefore, the displacement here, if they overlap perfectly, is the vector sum of the individual displacement, right? So it would be the two peaks, the two peaks added together, which would produce a bigger peak, right? That looks like this. And same with the trough, it would produce a bigger trough. This is called a constructive interference, right? And that is what would happen, and that's what the detector would detect, right? It would detect a constant and very bright brightness, right? If a gravitational wave passes through the interferometer, it would stretch space in one of the arms and compress the arm in the other direction, right? Yeah, it would compress the other arm, which means that, well, the waves would oops, I should probably get rid of this. Come on. Okay, give me back my two waves, please. Okay, so one of the waves, their path difference, right, would be different because they have to travel different distances, and since their velocity is the same, one of them would be more ahead and one of them would be more behind when they rejoin at the beam splitter, right? So in this case, or in this instance, they would be slightly, just ever so slightly out of phase, right, due to the gravitational wave. Therefore, where before there was beforehand, if you could recall, the peaks both overlapped at the same place, right? But now they're overlapping at different places. So what that means is that the displacement at any one point, according to the principle of superposition, is the vector sum of the individual displacement at that point, right? So just take this point, right? Beforehand, the two peaks were at the same place. Therefore, the the um, the overall displacement was the height of the two peaks added together. But now the displacement is different, right? As you can see, this part is not the peak anymore. Therefore, the displacement would be the two heights added together, which would be smaller now, right? So the overall brightness would be slightly, just ever so slightly dimmer than before, right? And you could take any point, right? You can take like the trough, right? It would be the same, because where there was two peaks before, there was a peak, and now there's a peak and a slightly lower height, right? And the detector is very intricate, and it can detect slight changes in brightness, right? And we're gonna go into a bit more depth of how they work. So you have a Fabry-Perot cavity in the interferometer. It's located somewhere over here in the interferometer. And what it does is it basically amplifies the effects of a gravitational wave, right? Because the effects of a gravitational wave on the lasers is very, very small. So you kind of want to increase its effects so that the detector can pick it up more easily. So here is a diagram, right? You have basically two concave lenses that splits the light, and the light in here would get rebounded many times, right? Then rebound or reflect off the mirrors multiple times before getting sent back out here. And an interference pattern would be formed here, okay? So, and obviously there would be multiple instant light rays, right? So they would all rejoin here. So the way that the distance between like the mirrors, the way that they're tuned is that if there's no gravitational waves going through the interferometer at that moment, then the light rays, they would the wavelength, right? That would be a default wavelength, and they would tune the Fabry-Perot cavity such that the default wavelength would cause it to have like a good resonance. It would form a good resonance here, right? So they would have a high resonance, which means that the all the waves that rejoin here would be pretty much in phase, right? And this is what it would look like, the interference pattern, right? It would have a high finesse. But if the wavelength of the light changes due to gravitational waves, stretching them, then they would not have a very high resonance here, right? And that means they would have a low finesse. So the interference pattern would look something like that, right? And so if gravitational waves pass through the interferometer, right, then they're going to have different finesse. Therefore, the interference pattern is going to be looking quite different, right, for these two separate lasers, right? So the interference pattern produced would be quite different, and when they rejoin, obviously they wouldn't match up perfectly, right? So the detector would pick up the difference in how they match up, right? So if they match up perfectly, then the brightness would be at its maximum. But if they don't, then the brightness could fluctuate a bit. And that is how you would detect it, or that's how the Fabry-Perot cavity enhances or amplifies the effects of the gravitational wave. So yeah, and obviously the interferometer you want it to be like as still as possible, right? You want all the conditions to be as constant as possible. You don't want any environmental factors to affect the results, right? So it has an active feedback system to maintain perfect phase alignment, right? It just what it does, it adjusts the mirror positions to counteract any tiny drifts or like distortions in the path of light rays or the optical path lengths due to like environmental factors, right? And it would also have a thermal compensation system, which like the laser here, it would be very, very high powered, right? So it might heat up the lenses, it might heat up the mirrors, it might heat up like this, right? It just what it does, the TCU, not TCU, sorry, TCS, is that so the high power lasers could heat up the optics slightly, which changes their refractive index, right, and causing tiny path length changes. So the TCS uses heaters and like adaptive optics and stuff to to minimize this effect, right? Which maintains the phases of the waves to ensure that the results are not compromised by the changes in temperature. So yeah, thank you for sticking with me throughout the video. I hope you've enjoyed the video and learned a bit more about interferometers and gravitational waves. And yeah, I'll catch you in the next one. Later.